Welcome. I'm so glad you found your way here tonight. Maybe you've had a long day filled with numbers and calculations, or maybe you're simply the kind of person who drifts off best when pondering the deep mysteries that sit quietly beneath everyday things. Either way, tonight's exploration is meant for you. A gentle journey through one of the most fascinating questions humanity has ever asked. Not about distant galaxies or ancient civilizations, though we'll touch on those. No, tonight we're asking something closer, something that lives in every moment you count, every time you measure, every instance you calculate. We're asking whether mathematics exists out there in the universe, waiting to be discovered like buried treasure, or whether we invented it piece by piece, symbol by symbol, creating it from nothing the way a poet creates a verse. It's a strange question, isn't it? Because mathematics feels so solid, so reliable. 2 plus 2 equals 4, whether you're in Tokyo or Tanzania, whether it's Tuesday or Thursday, whether you're awake or asleep. Mathematical truths seem eternal, unchanging, absolute. The Pythagorean theorem worked for ancient Greek geometers, and it works for modern architects. Pi has been the same number since before humans existed to calculate it. Prime numbers follow their mysterious patterns, whether anyone's watching or not. This permanence, this independence from human whims, makes mathematics feel discovered, as if we're explorers uncovering eternal truths that were always there, hidden in the fabric of reality itself. And yet, there's something undeniably human about mathematics. We invented the symbols. We created the notation. Different cultures developed different number systems, counted in different bases, approached calculation from different angles. The ancient Babylonians used base 60. The Mayans used base 20. We use base 10, probably because we have 10 fingers. Are these just different languages describing the same underlying reality? Like how different cultures have different words for sun, but they're all pointing at the same burning star? Or is mathematics itself a human creation, as cultural and contingent as language, as invented as poetry or music or chess? This isn't just an academic puzzle. It's a question that reaches into the nature of truth itself, into what it means for something to be real, into how we know anything at all. It's a question that has kept philosophers awake for thousands of years. And tonight, as you settle in and let your mind wander through the soft edges of sleep, we're going to explore it together. Not to find the answer, because honestly, no one has the answer, but to see what the journey reveals, to appreciate the strangeness and wonder of mathematics itself, to understand why this question matters and why it's so beautifully, maddeningly difficult to resolve. So get comfortable. Let your breathing slow. There's nowhere you need to be, nothing you need to solve. We're just going to drift through ideas together, examining them gently, turning them over like smooth stones found on a beach. We'll visit ancient civilizations and modern neuroscientists, meet philosophers and mathematicians, explore both sides of this ancient debate, and maybe, just maybe, find that the question itself is more interesting than any answer could be. Before we truly begin, if these calm explorations through mathematical mysteries help you unwind at the end of your day, consider liking and subscribing to the channel. It helps other curious, sleepy souls find their way here too, one restful mind at a time. Now let's begin our gentle journey into one of mathematics' deepest mysteries. Does math exist, or did we invent it? Let's find out what we can learn by asking. The ancient origins. When humans first counted, to understand whether mathematics was discovered or invented, it helps to go back, way back, before equations and theorems, before even written language, to a time when humans first began to count. Because counting, that simple human activity, is where mathematics begins. And the story of how different peoples learned to count tells us something profound about the nature of mathematical thought itself. Imagine you're living 30,000 years ago. The ice still covers much of Europe. You're part of a small group, maybe 30 or 40 people, surviving together in a world that's beautiful and brutal in equal measure. You need to keep track of things. How many days until the moon is full again? How many members in your hunting party came back? How many seasons have passed since you were born? And so you make marks, simple scratches on bone or wood or cave walls. One mark for each thing you're counting. Tally marks, we'd call them now. The most ancient form of mathematical notation we know. Archaeologists have found bones with these marks. The Lebombo bone, discovered in the Lebombo Mountains between South Africa and Swaziland, dates back about 43,000 years. It has 29 notches carved into it. 29, the same number of days in a lunar month. Was someone tracking the moon's cycle? We can't know for certain, but it seems likely. Here was someone, millennia before written language, before cities, before agriculture, already thinking mathematically, already using symbols to represent quantities, already recognizing patterns in nature and recording them. This is pure invention, right? Someone decided to make marks to represent things. They chose to carve rather than paint, chose bone rather than bark, chose this particular method of record keeping. Every part of it was a human decision, a human creation. And yet, the thing they were recording, the lunar cycle, that existed independently. The moon waxed and waned, whether anyone counted it or not. So even in this earliest mathematics, we see both creation and discovery intertwined. The notation is invented. The pattern being recorded exists independently. As human civilizations grew more complex, so did their need for more sophisticated mathematics. And here's where the story gets really interesting. Because all around the world, completely independently, different civilizations invented different number systems. Not just different symbols, but different approaches, different bases, different ways of thinking about quantity itself. In Mesopotamia, in the Fertile Crescent between the Tigris and Euphrates rivers, the ancient Sumerians and later the Babylonians developed something extraordinary, a number system based on 60, base 60, or sexagesimal as mathematicians call it. Why 60? Possibly because 60 has many divisors. You can divide it evenly by 2, 3, 4, 5, 6, 10, 12, 15, 20, and 30. This makes fractions much easier to work with. If you're dividing grain among workers or calculating areas of fields, a base with many divisors is incredibly useful. The Babylonians used a place value system, which was revolutionary. In a place value system, the position of a digit affects its value, just like in our modern system, where the 2 in 20 means something different than the 2 in 200. The Babylonians were doing this 4,000 years ago. They used combinations of 2 symbols, 1 for 1 and 1 for 10, arranged in different positions to represent any number they needed. And remarkably, we still use their base 60 today. 60 seconds in a minute, 60 minutes in an hour, 360 degrees in a circle. Every time you check the time or measure an angle, you're using Babylonian mathematics. Over in Egypt, along the Nile, a completely different system evolved. The Egyptians used a base 10 system, probably because of our 10 fingers, but they didn't have place value. Instead, they had different hieroglyphic symbols for 1, 10, 100, 1000, and so on. To write 347, you draw 3 symbols for 100, 4 symbols for 10, and 7 symbols for 1. It's cumbersome compared to what came later, but it worked for their needs. They built pyramids with it. They calculated the flooding of the Nile. They developed practical geometry to resurvey fields after floods washed away boundary markers. Across the Pacific, the Maya civilization developed yet another system, completely independently. They used base 20, probably because they counted on fingers and toes. But they also did something incredibly sophisticated. They invented zero, not just as a placeholder, but as a concept, as a number in its own right. This happened around the 4th century CE, and it was a profound leap in mathematical thinking. The Maya needed zero because they had a positional system, and in a positional system, you need a way to show that a position is empty. But zero is more than just a practical tool. It's a philosophical statement. It says that nothing, absence, emptiness, can be represented and manipulated mathematically. That nothingness is something. In China, mathematicians developed a decimal system using rod numerals and counting boards. They had different orientations for different positions to avoid confusion. Vertical rods for units and hundreds, horizontal for tens and thousands. Red rods for positive numbers, black for negative. The Chinese were among the first to use negative numbers systematically, another conceptual leap. How do you have less than nothing? How do you represent debt, or temperature below freezing, or movement backwards? The Chinese answer was to extend the number line in both directions from zero, treating negative numbers as just as real as positive ones. And in ancient India, perhaps the most consequential mathematical development of all, Indian mathematicians, building on ideas that had circulated for centuries, fully developed the concept of zero and integrated it into a complete positional decimal system. This is the system we use today. 10 digits, including zero, with position determining value. The Hindu-Arabic numerals, they're called, because Indian mathematicians developed them and Arab scholars transmitted them to Europe. This system is so elegant, so efficient, that once it arrived in Europe in the Middle Ages, it quickly replaced Roman numerals for calculation, though Roman numerals persisted for decoration and ceremonial uses. Now, here's the philosophical puzzle. Hiding in this history, all of these civilizations independently invented number systems, but they all invented systems that work. You can translate between them. You can calculate in Babylonian base 60, convert to Egyptian hieroglyphs, then to Mayan base 20, then to Chinese rod numerals, then to Hindu-Arabic decimals, and you'll get the same answer. The notation is different, the approach is different, but the underlying mathematical truth is the same. 3 sheep are 3 sheep, whether you write it in cuneiform, hieroglyphs, or modern numerals. This suggests something important. The notation is clearly invented. The The symbols are human creations, varying from culture to culture. But the thing the notation describes, quantity itself, seems to exist independently of our descriptions. 7 really is 7, not because we decided it should be, but because there's something objective about the difference between 7 sheep and 8 sheep, between 7 days and 8 days. The symbols we use to represent 7 are arbitrary, conventional, invented, but sevenness itself, the quality of being 7, seems to be discovered, or does it? Because you could argue that quantity itself is a human concept, that we group things into discrete units, but nature doesn't. When you say 7 sheep, you're imposing categories onto a continuous reality. The sheep are individuals, each unique, each slightly different. By calling them all sheep and counting them, you're abstracting away their individuality, treating them as identical units, which they're not. You're creating the category sheep and then counting members of that category. Nature doesn't do this. Nature doesn't count. Only minds count. This is the beginning of the puzzle. Even in the most basic mathematics, in simple counting, we find this strange interplay between creation and discovery. The tools we use, the notations and systems, are clearly invented. Different cultures proved this by inventing different ones. But the truths those tools allow us to describe seem independent of the tools themselves. The Pythagorean theorem, which states that in a right triangle, the square of the hypotenuse equals the sum of the squares of the other two sides, was known to the Babylonians centuries before Pythagoras. They didn't phrase it the same way. They didn't have the same notation, but they knew it. They used it to calculate. The truth of the relationship was there, waiting to be found, even though the specific formulation was invented. So we're left with a question that our ancient ancestors, carving marks into bone by firelight, probably never considered but implicitly answered with every scratch. When humans began to count, were they inventing mathematics or discovering it? Were they creating something new or finding something that was already there? The notches on the Lubombo bone, the cuneiform tablets of Babylon, the hieroglyphs of Egypt, the Mayan codices, the Chinese counting boards, the Indian manuscripts, they all testify to the human capacity for mathematical thinking. But do they testify to human creativity or to human insight into an independent mathematical reality? We'll explore both possibilities. But first, let's meet one of the most influential philosophers in history, a man who had very strong opinions about whether mathematics exists independently of human thought. His name was Plato, and his answer to our question shaped Western philosophy for 2,000 years. Plato's Eternal Forms, the case for discovery. If you had asked Plato whether mathematics exists or was invented, he would have looked at you as if you'd asked whether the sun exists. Of course mathematics exists, he would have said, and not just exists in some wishy-washy metaphorical sense, really exists, perhaps more truly than the physical world we perceive with our senses. To understand why Plato thought this, and why many mathematicians still feel the same pull toward this view, we need to understand his theory of forms. Plato imagined, or perhaps believed, that there exists a realm of perfect, eternal, unchanging abstract objects. Not physical objects, not things you can touch or see with your eyes, but real nonetheless. Forms, he called them, or ideas in the original sense of that word. The Greek word eidos, meaning something like pure essence or perfect exemplar. For every category of thing in the physical world, Plato believed there was a perfect form in this abstract realm: the form of a horse, the form of beauty, the form of justice, and crucially, the form of mathematical objects, the form of circle, the form of triangle, the form of the number 3. The physical world, according to Plato, is just a shadow of this realm of forms. When you draw a circle on paper, you're not really drawing a circle. A real circle, a perfect circle, has every point on its circumference exactly the same distance from the center. Your drawn circle, no matter how carefully you draft it, has imperfections. The line has width. The points aren't precisely positioned. Under a microscope, it looks jagged and irregular. But we can reason about perfect circles. We can prove things about them. And the truths we discover apply to an idealized circle that exists nowhere in the physical world, but everywhere in the realm of forms. For Plato, doing mathematics was exploring this realm of forms. A mathematician doesn't invent circles. She discovers truths about the eternal form of circle. She doesn't create the number 7. She finds out properties that 7 has always had and will always have. Mathematical truth, in this view, is discovered the same way a geologist discovers rock formations, or an archaeologist discovers ancient cities. It's uncovering something that was already there, hidden, waiting. This view is called mathematical Platonism, and it's remarkably popular among working mathematicians, not because they've all read Plato, though some have, but because it captures something about the phenomenology of doing mathematics. When a mathematician proves a theorem, it often feels like discovery, not invention. It feels like the theorem was true all along, and the mathematician's job was to uncover this truth, to forge a logical path from axioms to conclusion that reveals something that already existed. Consider the prime numbers. A prime number is a natural number, greater than 1 that can't be divided evenly by any number except 1 and itself. So 2, 3, 5, 7, 11, 13, and so on. Primes have fascinated mathematicians for thousands of years because they seem to be the building blocks of all numbers. Every number is either prime or can be broken down into a unique combination of primes. This is called the fundamental theorem of arithmetic. Now, there are infinitely many prime numbers. We've known this since Euclid proved it around 300 BCE. His proof is elegant and beautiful, showing that no matter how many primes you've found, there must be more. But the distribution of primes is mysterious. As you count higher and higher, primes become less frequent, but they never completely stop appearing. They seem scattered almost randomly through the integers, yet patterns emerge. The famous Goldbach conjecture, still unproven, states that every even number greater than 2 can be expressed as the sum of 2 primes. The Riemann hypothesis, one of the great unsolved problems in mathematics, relates to how primes are distributed. When a mathematician studies primes, does it feel like she's inventing them? Or does it feel like she's exploring a landscape that exists independently, discovering features of this landscape, mapping territory that was always there? Most mathematicians will tell you it feels like the latter. Primes feel discovered. Their properties feel like facts about the world, or at least facts about an abstract mathematical world that's just as real as the physical one. Or consider pi, the ratio of a circle's circumference to its diameter. This number is the same for every circle everywhere in the universe. It can't be expressed as a fraction. Its decimal expansion goes on forever without repeating. 3.141592653589979. On and on and on. We've calculated pi to trillions of digits. Did we invent this number? Or was it always there, lurking in the nature of circles, waiting for humans to come along and approximate it better and better? The Platonist says pi was always there. It's a necessary consequence of the definition of a circle and the nature of geometric space. Any being anywhere in the universe that develops geometry and defines circles will discover the same pi. This suggests that pi is real in some deep sense. Not physically real, you can't stub your toe on pi, but abstractly real, existing in a realm of mathematical objects that transcends any particular mind or culture. The same argument applies to more complex mathematics. The Mandelbrot set, that intricate, beautiful fractal discovered by Benoit Mandelbrot in 1980, was the same before Mandelbrot discovered it as it is now. The set is defined by a simple mathematical rule applied iteratively. The rule was always valid. The set it generates was always the same. Mandelbrot didn't invent the Mandelbrot set any more than Columbus invented America. He discovered it. He was the first human to see it, because he was the first to have the right computational tools and the right question in mind. But it was there all along, implicit in the mathematics, waiting. This is the strength of Platonism. It explains why mathematics feels the way it does to mathematicians. It explains why mathematical truths seem necessary and universal. It explains why different mathematicians, working independently, often discover the same theorems, because they're not inventing personal mathematical systems. They're all exploring the same abstract realm, the same landscape of mathematical truth. Platonism also explains something called the unreasonable effectiveness of mathematics in the natural sciences. We'll explore this more deeply soon, but the basic observation is startling. Mathematics developed abstractly, for its own sake, often turns out to perfectly describe physical reality. The mathematics of complex numbers, invented to solve otherwise unsolvable equations, turned out to be essential for quantum mechanics. Group theory, developed as abstract algebra, turned out to be crucial for understanding particle physics. Einstein's general relativity required Riemannian geometry, which was developed decades earlier as pure mathematics with no application in mind. How can abstract mathematics, invented or discovered in the minds of people sitting in studies, describe the behavior of the physical universe so accurately? The Platonist has a ready answer. Because mathematical objects really exist, and the physical universe is structured according to mathematical principles, the universe is, in some sense, mathematical. And so mathematical truth and physical truth are aligned. Not because we cleverly designed mathematics to match physics, but because both mathematics and physics answer to the same underlying reality. This is heady stuff. It's also, many philosophers argue, more than a little strange. Because if mathematical objects really exist in some abstract realm, how do we know about them? We can't see them with our eyes. We can't touch them with our hands. We can't detect them with scientific instruments. How does the human mind, locked in a physical skull, in a physical universe, gain access to this realm of abstract forms? Plato himself struggled with this. He eventually suggested that the soul had existed in the realm of forms before being born into a body, and that learning mathematics was actually remembering truths the soul already knew. This is a poetic answer, perhaps, but not one that convinces many modern philosophers. If mathematical objects exist outside space and time, outside the causal order of the physical universe, then it seems impossible for us to have any knowledge of them. And if we can't know anything about them, how can we do mathematics at all? This is called the epistemological problem for Platonism. Epistemology is the branch of philosophy concerned with knowledge. How do we know what we know? What makes a belief justified? The Platonist seems to have a problem here. They claim mathematical objects exist in an abstract realm, causally disconnected from us. But then how do we have mathematical knowledge? How do we form true beliefs about these abstract objects? Some Platonists bite the bullet and say we have a special faculty of mathematical intuition. Just as we have eyes to perceive physical objects, we have some kind of intellectual perception to grasp mathematical truths. This doesn't satisfy everyone. It seems to create more mysteries than it solves. What is this faculty? How does it work? Why should we trust it? Other Platonists take a different approach. They argue that the epistemological problem is overblown. We don't need direct causal contact with something to have knowledge of it. We can reason about abstract objects using logic and proof. As long as our reasoning is valid, we can be confident in our conclusions. Yes, mathematical objects are abstract and causally inert. But that doesn't prevent us from describing them, axiomatizing their properties, and deriving conclusions. In fact, it's precisely because they're abstract that we can have such certain knowledge. They don't change. They don't behave unpredictably. Unlike physical objects, which we know only through uncertain sensory perception, mathematical objects can be known with perfect clarity through pure reason. Still, the problem gnaws, and it leads some philosophers and mathematicians to reject Platonism entirely. If mathematical objects don't exist in any real sense, if mathematics is pure invention, human creation through and through, then the epistemological problem vanishes. We can know about mathematics because we made it. We have access to mathematical objects because they exist only in our minds. This is the anti-Platonist position, and it has its own appeal and its own problems. But before we explore the alternatives to Platonism, there's one more aspect of the Platonist view worth considering: its sheer wonder, its celebration of mathematics as something greater than ourselves. In Plato's vision, mathematics connects us to something eternal, perfect, unchanging. When we prove a theorem, we touch infinity. When we grasp a mathematical truth, we transcend our limited, finite, mortal existence and make contact with the absolute. This is not a small thing. Many mathematicians speak of beauty in mathematics, elegance, even awe. They describe certain proofs as beautiful, not in a metaphorical sense, but viscerally, emotionally, the way one might find a sunset or a symphony beautiful. And this beauty seems to point to something beyond human convention. A joke is funny because of our psychology and culture. What's hilarious in one language might be meaningless in another. But mathematical beauty seems universal. Euler's identity, the equation that links 5 of the most important numbers in mathematics, e to the power of pi times I plus 1 equals 0, is considered beautiful by mathematicians across all cultures. Why? Because it seems to reveal a deep connection between seemingly unrelated mathematical objects, a connection that was always there, waiting to be found. The Platonist view honors this sense of wonder. It says, yes, mathematics is bigger than we are. It's older than human civilization. It will outlast our species. The truths of mathematics would be true even if intelligent life had never evolved. They're woven into the structure of reality itself, or perhaps they are the structure of reality. And our privilege, our joy, is to discover these truths one by one, theorem by theorem, proof by proof. It's a compelling vision, but it's not the only one. And as we drift deeper into our exploration tonight, we'll meet other views that place human creativity at the center, views that see mathematics not as discovered, but as invented, not as eternal, but as historical, not as transcendent, but as gloriously, beautifully human. Let's see what they have to say. The unreasonable effectiveness. Why math works so well. 1960, a physicist named Eugene Wigner published an essay with a peculiar title, The Unreasonable Effectiveness of Mathematics in the Natural Sciences. In it, Wigner explored a phenomenon that he found deeply puzzling, almost miraculous. Mathematics, developed often as pure abstraction with no thought of physical application, has an uncanny ability to describe the natural world with stunning precision. Not approximately, not roughly, but exactly, down to absurd levels of detail. This observation has philosophical teeth, because if mathematics is just a human invention, something we made up for convenience or cultural reasons, why should it describe reality so perfectly? Why should the universe care about our conventions, our symbols, our invented frameworks? It would be like discovering that English grammar perfectly describes the orbits of planets, or that the rules of chess predict how plants grow. Absurd. And yet, that's essentially what we find with mathematics. Let's look at some examples. Because this isn't abstract philosophical speculation. It's concrete, observable, repeatedly confirmed by the entire history of physics. Start with Isaac Newton. In the 1600s, Newton was trying to understand motion. Why do apples fall? Why do planets orbit? He developed calculus, a mathematical tool for describing rates of change, and used it to formulate his laws of motion and universal gravitation. These laws said that every object attracts every other object with a force proportional to their masses and inversely proportional to the square of the distance between them. This was based on very scanty observations, as Wigner put it, some astronomical data, some experiments with falling objects. Yet Newton's laws turned out to be astonishingly accurate, predicting planetary motions centuries into the future, explaining tides, comets, the shape of the Earth, all from a handful of mathematical equations. Or consider James Clerk Maxwell. In the 1860s, Maxwell was studying electricity and magnetism. These had been investigated experimentally for decades. People knew how electric currents behave, how magnets attract and repel. Maxwell tried to unify these phenomena mathematically. He wrote down 4 equations, now called Maxwell's equations, that describe all of classical electromagnetism. These equations were beautiful, symmetric, elegant. But here's the remarkable thing. When Maxwell solved these equations, he found they predicted the existence of electromagnetic waves that travel at a specific speed. That speed turned out to be the speed of light. This led Maxwell to propose that light itself is an electromagnetic wave, but the mathematics went further. Maxwell's equations don't just describe visible light. They describe electromagnetic radiation at all frequencies: radio waves, microwaves, infrared, ultraviolet, X-rays, gamma rays. None of these were known when Maxwell wrote down his equations. He had no experimental evidence for them, yet his equations predicted them. And within decades, all of them were discovered, exactly as the mathematics suggested. Think about that. A man sitting in his study, manipulating symbols on paper according to logical rules, predicted the existence of phenomena no one had ever observed. And then those phenomena were found, behaving exactly as the equations said they would. How? Why? If mathematics is just a game of symbols, a human invention with no necessary connection to physical reality, this seems impossible. The examples multiply. Albert Einstein, developing his theory of general relativity, needed to describe how gravity works in a new way. He needed mathematics to describe curved spacetime. Fortunately, decades earlier, mathematicians had developed non-Euclidean geometry and Riemannian geometry, tools for describing curved spaces. They developed these as pure mathematics, explorations of logical possibilities, with no thought of physical application. Yet they turned out to be exactly what Einstein needed. The mathematics existed before the physics required it, and general relativity, in turn, made predictions that seemed outlandish. It predicted that massive objects warp spacetime, bending the path of light. It predicted that orbits would precess in specific ways. It predicted the existence of black holes, regions where spacetime curves so extremely that not even light can escape. It predicted that accelerating masses would produce gravitational waves, ripples in spacetime itself. All of these predictions came from the mathematics, and all of them, over the decades and centuries following Einstein's work, were confirmed. Gravitational waves were finally detected in 2015, a century after Einstein predicted them, detected exactly as the equations said they would be, or quantum mechanics. In the early 20th century, physicists were baffled by the behavior of atoms and subatomic particles. Nothing made sense. Particles seemed to be waves. Measurements gave probabilistic rather than definite answers. Classical physics was failing. Then physicists started using mathematics that had been developed for other purposes: complex numbers, linear algebra, Hilbert spaces, group theory. These mathematical tools, abstract and seemingly irrelevant to physics, turned out to be perfect for describing quantum phenomena, and quantum mechanics is now the most precisely tested theory in all of science. Its predictions match experiments to absurd levels of accuracy. The magnetic moment of the electron, for example, has been calculated using quantum electrodynamics and measured experimentally, and they agree to 11 decimal places, not approximately, not in the right ballpark, exactly, to 11 decimal places. How does abstract mathematics do this? Wigner found this unreasonable. He couldn't explain it. The mathematical formulation of physics leads to predictions that are confirmed with an uncanny accuracy, he wrote. The effectiveness of mathematics is something bordering on the mysterious, and there is no rational explanation for it. Let's think about why this is so puzzling, particularly if you believe mathematics is invented rather than discovered. Suppose mathematics is just a human tool, like language or a hammer. Different cultures might develop different mathematics. different systems of symbols and operations suited to their particular needs and ways of thinking. And indeed, we've seen that different cultures did develop different number systems. But here's the catch. When we use our mathematics, our particular human conventions, to describe nature, nature cooperates. The universe doesn't shrug and say, "Sorry, I operate by different rules." The universe responds. The mathematics works. Why? One possible answer, the Platonist answer, is that mathematics isn't invented at all. It's discovered. Mathematical truths are facts about an abstract realm, and physical reality is structured according to these same mathematical principles. The universe is mathematical. It operates according to mathematical laws because mathematical truth is, in some deep sense, what determines physical possibility. Gravity obeys an inverse square law, not because we invented that law, but because that's how reality is structured, and the structure is mathematical. This would explain why abstract mathematics, developed without any thought of physics, nevertheless applies to physics. The mathematicians and physicists are exploring the same structure from different angles. The mathematician explores it purely logically, seeing what follows from axioms. The physicist explores it through observation and experiment, seeing what the universe does. But they meet in the middle because the structure itself is what's real. But there's another possible explanation, and it's less mysterious, though perhaps less satisfying. Maybe mathematics is effective not because it describes a pre-existing mathematical structure to reality, but because we've selectively remembered and developed the mathematics that turned out to be useful. Throughout history, mathematicians have explored countless ideas. Most of them went nowhere. They were beautiful, perhaps, or interesting as puzzles, but they didn't connect to anything else or prove useful. Those parts of mathematics were forgotten or marginalized. Only the mathematics that proved useful survived and flourished. So when we look back at the history and marvel at how often abstract mathematics turned out to apply to physics, we're suffering from selection bias. We're only looking at the successes, the mathematical tools that didn't work, that didn't describe nature, faded into obscurity. Of course, the mathematics that's still around is effective. It survived precisely because it was effective. It's not miraculous. It's just survivor bias. This argument has some force, but it doesn't quite dispel the mystery, because the successes are really astonishingly precise, and they often involve mathematics developed with absolutely no hint that it might be physically relevant. Group theory, for instance, was developed in the 19th century to solve purely algebraic problems. It's about symmetries and transformations, abstract patterns, yet it turned out to be essential for particle physics, where it describes the symmetries underlying fundamental forces. The mathematician who developed group theory had no inkling of quarks or gluons, yet his abstract explorations mapped perfectly onto the structure of matter. Moreover, the selection bias argument doesn't explain why some mathematics keeps being useful again and again in completely different contexts. Complex numbers, for example, were invented to solve cubic equations. Then they proved essential in wave mechanics, then in electrical engineering, then in quantum mechanics, then in signal processing and control theory, and fluid dynamics, and on and on. It's not that we kept one tool because it was useful once. We kept it because it was useful over and over in wildly different domains. The same mathematical structure kept showing up in nature, in contexts no one anticipated. There's something else to consider. Physics isn't just about describing what we observe. It's about predicting what we haven't observed yet. And here, mathematics shines most brightly. When physicists derive equations from fundamental principles, those equations make predictions, and routinely, startlingly, those predictions are confirmed. Maxwell predicted radio waves. Einstein predicted gravitational waves. Dirac predicted antimatter. Higgs predicted the Higgs boson. All of these came from the mathematics, from sitting down and solving equations before any experimental evidence. If mathematics were just a convenient description of what we've already seen, it wouldn't predict genuinely new phenomena with such reliability. So Wigner's question persists. Why is mathematics so unreasonably effective? The Platonist has a clear answer. Because mathematics describes the structure of reality, and reality is fundamentally mathematical. The anti-Platonist has to work harder, invoking selection bias and contingent historical development. Neither answer fully satisfies. The mystery lingers, beautiful and unresolved, and there's a flip side worth mentioning. While mathematics is unreasonably effective in physics, it's far less effective in other sciences. Biology, for instance, uses mathematics, but not with the same precision or predictive power. You can't derive the structure of an ecosystem from first principles the way you can derive planetary orbits. Economics uses mathematics extensively, but economic models routinely fail to predict real-world behavior. Psychology, sociology, even chemistry to some extent. These fields benefit from mathematics, but don't achieve the level of mathematical description that physics enjoys. This suggests something about physics specifically, not just about mathematics in general. Maybe physics is the study of those aspects of reality that happen to be mathematically tractable. Everything else, the messy, complex, contingent aspects, those require different approaches. Mathematics works brilliantly where it works, but its domain may be more limited than the Platonist hopes. Still, even in that limited domain, the effectiveness is astonishing. And for the Platonist, it's evidence, not proof, but strong evidence. If mathematics were merely invented convention, the fact that it describes nature so well would be an inexplicable coincidence. But if mathematics is discovered, if mathematical objects and structures really exist, and the physical universe is built according to these structures, then the effectiveness makes sense. It's not a coincidence. It's the expected outcome. As we continue our journey through this question, through the philosophy of mathematics, we'll keep returning to this puzzle. The unreasonable effectiveness of mathematics is one of the strongest arguments for Platonism, for the idea that mathematics is discovered rather than invented. But it's not the only consideration. And now we'll turn to views that take the opposite stance, views that insist mathematics is invented through and through, human creation from top to bottom. Let's see what they have to say about effectiveness and everything else. The formalist view, math as a game of symbols. Imagine mathematics as a game, a very sophisticated game with complex rules, but a game nonetheless. The pieces are symbols, numerals, variables, operators, logical connectives. The rules are axioms and inference rules, the basic assumptions and allowed moves. A mathematical proof is a series of moves, each step justified by the rules, leading from the starting position, the axioms, to the endgame, the theorem. The whole enterprise has no meaning beyond the game itself. The symbols don't refer to anything. They're just marks on paper or pixels on a screen. Mathematics is the art of manipulating these symbols according to fixed rules. This is the formalist view of mathematics, and for a time in the early 20th century, it was highly influential. The formalist doesn't deny that mathematics is useful. Of course it's useful. Games can be useful. Chess teaches strategy and planning. Crossword puzzles improve vocabulary. Mathematical formalisms prove incredibly useful for describing and predicting physical phenomena. But the usefulness doesn't mean the symbols refer to real abstract objects. It just means the game happens to have applications. To understand formalism, it helps to know a bit about the history. In the late 19th and early 20th centuries, mathematics was in crisis. Paradoxes had been discovered in the foundations of set theory. The most famous is Russell's paradox. Consider the set of all sets that don't contain themselves. Does this set contain itself? If it does, then by definition it shouldn't. If it doesn't, then by definition it should. Either way leads to contradiction. This was a problem. Set theory was supposed to be the foundation of all mathematics. If it contained contradictions, the whole edifice was shaky. Mathematicians responded in different ways. Some, like Bertrand Russell and Alfred North Whitehead, tried to reconstruct mathematics on a firmer logical foundation. Others, the intuitionists, rejected large swathes of traditional mathematics as unjustified. And then there were the formalists, led by David Hilbert, one of the greatest mathematicians of all time. Hilbert's idea was to formalize mathematics completely, to reduce it to a system of symbols and rules with no ambiguity, no hidden assumptions, no reliance on intuition or meaning. Mathematics would become a formal game. And the only question would be whether a given string of symbols could be derived from the axioms using the allowed rules. Meaning wouldn't enter into it. The symbols wouldn't represent anything. They'd just be tokens in a game. This might sound like it empties mathematics of content, and in a sense, it does. But Hilbert saw it as a virtue. If mathematics is purely formal, then it's immune to philosophical disputes about what mathematical objects are or whether they exist. It doesn't matter. The symbols exist, certainly. They're physical marks, and the rules exist as conventions we've agreed upon. That's enough. We can do mathematics, derive theorems, without committing to any metaphysical claims about numbers or sets or functions existing in some abstract realm. The formalist program had a few key components. First, mathematics would be reduced to a formal system, a collection of symbols, formation rules for how symbols can be combined, axioms, and inference rules. Second, we'd prove that this formal system is consistent, that it can't derive a contradiction. Third, we'd prove that it's complete, that every true mathematical statement can be proven within the system. If these goals were achieved, mathematics would be on rock-solid foundations. No more paradoxes, no more confusion, just rules and derivations. The program was ambitious, and tragically, it failed. In 1931, Kurt Gödel, a young Austrian mathematician, proved two incompleteness theorems that shattered Hilbert's dream. The first theorem showed that any formal system rich enough to include arithmetic will contain statements that are true but unprovable within the system. In other words, there's no complete formal system for mathematics. There will always be truths that escape formalization. The second theorem showed that no consistent formal system can prove its own consistency. So even the goal of proving mathematics consistent was unreachable from within mathematics itself. Gödel's theorems were a blow to formalism, but they didn't kill it entirely. Some mathematicians and philosophers still find formalism attractive, even in a weakened form. They might concede that mathematics can't be fully formalized in the way Hilbert hoped, but they still maintain that mathematical activity is fundamentally about manipulating symbols according to rules. The symbols might not have meaning in the traditional sense, but they form a coherent system, and that system is mathematics. Now, you might wonder how formalism can account for the effectiveness of mathematics in science. If mathematics is just a meaningless game of symbols, why does it describe nature so well? The formalist has an answer, though not everyone finds it satisfying. The symbols themselves are meaningless, but we can interpret them, give them meaning, when we apply mathematics to the real world. When a physicist uses equations to describe motion, she's mapping the formal system onto physical phenomena. The equation F equals MAE doesn't mean anything within pure mathematics. It's just a string of symbols. But when we interpret F as force, M as mass, and A as acceleration, and when we apply the equation to actual objects, it becomes a powerful descriptive tool. So mathematics is effective because we've developed formal systems that, when interpreted, turn out to match patterns in nature. This is partly by design. We developed physics specifically to describe nature. So of course, we chose formalisms that fit. But it's also partly surprising, as with the cases Wigner discussed, where abstract mathematics developed for pure reasons later found physical applications. The formalist might say these are happy accidents, or perhaps they reflect something about human psychology. The way our minds structure thought tends to align with the way nature is structured, not because of any deep metaphysical connection, but because our minds evolved in nature and so have been shaped to recognize certain patterns. There's something appealing about formalism. It's austere, economical, no nonsense. It doesn't require belief in an abstract realm of mathematical objects. It doesn't need to explain how we access such a realm. It reduces mathematics to what we actually do: manipulate symbols, follow rules, derive consequences, and it aligns with a broadly naturalistic worldview that's skeptical of abstract objects and prefers to work with concrete, observable things like marks on paper or states of computers. But formalism also has problems. For one thing, it seems to miss something important about the mathematical experience. When a mathematician proves that there are infinitely many primes, she doesn't feel like she's playing a meaningless game. She feels like she's discovered a truth about numbers. Numbers that have properties, whether anyone's proving theorems about them or not. The formalist says this feeling is an illusion, or at least not to be taken at face value. But that's a hard pill to swallow. Moreover, there's a question about the rules themselves. In formalism, mathematics is defined by a formal system of axioms and inference rules. But where do these axioms and rules come from? Did we just invent them arbitrarily? Clearly not. The axioms of arithmetic or set theory aren't random. They capture something. They reflect intuitions about how numbers or sets should behave. But if the axioms are chosen to capture these intuitions, then we're back to talking about numbers and sets as if they have properties independently of the formal system. The formalism seems to presuppose exactly what it's trying to avoid. There's also a problem with meaning. Mathematics is full of meaning, rich with concepts and connections. The Pythagorean theorem isn't just a string of symbols. It's about relationships between the sides of right triangles, about the structure of Euclidean space. Category theory isn't just symbol manipulation. It's about morphisms and functors and the deep connections between different mathematical structures. To reduce all of this to meaningless tokens in a formal game seems to throw out the baby with the bathwater. Still, formalism remains influential, particularly in certain corners of mathematical logic and computer science. In computer science especially, the idea that mathematics is computation, symbol manipulation according to rules, has been fruitful. A computer program is, after all, a formal system, and much of mathematics can be implemented algorithmically, turned into procedures that a computer can execute. If mathematics really were discovered rather than invented, it's odd that we can mechanize it so thoroughly. So formalism offers an alternative to Platonism. Instead of saying mathematics is about an abstract realm we discover, the formalist says mathematics is a game we invented, a rule-governed activity with no necessary connection to anything outside itself. It's a bold position, and it has virtues, but it also has costs, and not everyone is willing to pay them. Let's keep moving, exploring other views that try to stake out different territory in this philosophical landscape. The intuitionist position. Math as mental construction. Here's a different way to think about mathematics. Not as an abstract realm we discover, and not as a meaningless game we play, but as a constructive activity. Mathematics, in this view, is something we build in our minds. Mathematical objects exist, yes, but they exist as mental constructions. A mathematician creates mathematical entities through a process of mental activity, through reasoning and intuition. And a mathematical statement is only true if we've actually constructed a proof of it. This is intuitionism, a philosophical position that emerged in the early 20th century, championed by the Dutch mathematician L.E.J. Brouwer. Intuitionism is subtle and sometimes counterintuitive. No pun intended. But it's based on a few key insights. First, intuitionism takes seriously the idea that mathematics is a human activity. When we do mathematics, we're not passively observing eternal truths. We're actively constructing mental entities, building mathematical objects through a process of thought. A natural number, for instance, isn't an abstract object existing in a Platonic heaven. It's something we construct by starting with 1 and repeatedly adding 1. 2 is 1 plus 1. 3 is 2 plus 1, and so on. Each number is built step by step from previous numbers and the primitive idea of succession. Second, intuitionism has a distinctive view about mathematical truth. For the Platonist, a mathematical statement is true if it corresponds to facts about abstract objects. 7 is prime is true because the abstract number 7 has the property of primality. But the intuitionist says truth is different. A mathematical statement is true if we've constructed a proof of it. Not if it could be proved in some abstract sense, but if we've actually constructed a proof. And crucially, for a statement to be false, we need to have constructed a proof of its negation. This leads to a striking consequence. For the intuitionist, not every statement is either true or false. In classical logic, the law of excluded middle says that for any statement P, either P is true or not P is true. But the intuitionist rejects this. Unless we've constructed a proof of P or constructed a proof of not P, we can't assert that one or the other is true. The statement might be in a kind of limbo, neither proven true nor proven false. Why would anyone believe this? Because the intuitionist says, truth is not something that exists independently of our knowledge. To assert that a statement is true is to claim that we have, or at least could have, a proof. And if we haven't constructed a proof, we're not entitled to assert truth. Existence in mathematics is tied to our ability to construct. To say there exists a number with property x is to claim that we can actually construct such a number, not just that one exists in some abstract sense. This changes how mathematics is done. In classical mathematics, you can prove that something exists by deriving a contradiction from assuming it doesn't exist. This is called a proof by contradiction, or an indirect proof. The intuitionist rejects these, or at least treats them more carefully. To prove existence, you need a direct construction, an actual method for producing the object in question. For example, in classical mathematics, you might prove there exists an irrational number by assuming all numbers are rational and deriving a contradiction. But for the intuitionist, that's not enough. You need to actually construct an irrational number, like the square root of 2, and show that it's irrational. The proof has to be constructive. This sounds restrictive, and it is. A lot of classical mathematics can't be done in intuitionism, or has to be redone differently. But intuitionists argue this is a feature, not a bug. Mathematics becomes more meaningful, more grounded in actual constructions and procedures, less reliant on dubious metaphysics about abstract objects existing somewhere. Intuitionism also has interesting things to say about infinity. For the Platonist, infinite sets exist, completed totalities of infinitely many objects. The set of all natural numbers is a finished, complete entity. But for the intuitionist, infinity is always potential, not actual. We can't complete an infinite process. We can start constructing the natural numbers, 1, 2, 3, and so on. And this process has no end. But we never have the completed infinite set. We just have the process, extending as far as we've taken it and capable of being extended further. This makes the intuitionist wary of reasoning about infinite sets as if they were finished objects. Cantor's work on different sizes of infinity, for example, becomes problematic. The intuitionist doesn't deny that some infinities seem larger than others in certain senses, but the whole framework of completed infinite sets is rejected. Now, intuitionism is a minority position in the philosophy of mathematics. Most working mathematicians are not intuitionists. They use classical logic, including proof by contradiction and the law of excluded middle. They talk about infinite sets without qualms. But intuitionism has influenced certain areas, particularly constructive mathematics and type theory, which are used in computer science for proof assistance and verified software. One reason intuitionism isn't more popular is that it seems to sacrifice too much. Classical mathematics is rich and beautiful, and much of it relies on methods the intuitionist rejects. The intermediate value theorem, for instance, which says that a continuous function that's positive at one point and negative at another must cross zero somewhere, can be proven classically, but not intuitionistically, without additional assumptions. Similarly, much of real analysis, the rigorous study of calculus, becomes more difficult in intuitionism. But from the intuitionist perspective, these sacrifices are worth it. Classical mathematics may be rich, but it's also filled with commitments to abstract objects and principles, like the law of excluded middle, that aren't justified. Better to have a smaller, more secure mathematics built on solid intuitions about what we can actually construct. Intuitionism also offers a response to the epistemological problem that plagues Platonism. How do we know about abstract mathematical objects if they exist in a causally disconnected realm? The intuitionist says we don't need to answer this question because there are no such objects. Mathematical objects exist in our minds as constructions. We know about them because we created them. There's no mystery about access. The mental construction is the object. Of course, this raises its own questions. If mathematical objects are mental constructions, are they private to each individual? When you think of the number 3, and I think of the number 3, are we thinking of the same thing? The intuitionist needs to explain how mathematical truth is objective and shared if mathematics is mental. Brouwer leaned toward a kind of solipsistic view where each mathematician constructs their own mathematics, but most intuitionists today are more cautious, arguing that while mathematical activity is mental, it's also intersubjective. We can communicate our constructions, compare them, and agree on standards of proof. Another criticism is that intuitionism seems to make mathematics dependent on human psychology in ways that feel wrong. If mathematical truth is about what we've constructed mentally, then does mathematics change as we discover new proofs? Classical mathematicians feel that the Pythagorean theorem was true before Pythagoras proved it. But the intuitionist seems committed to saying it became true only when Pythagoras or someone else constructed a proof. Some intuitionists embrace this. They say mathematics is a historical, evolving discipline. Mathematical truth grows as we construct more proofs. This isn't relativism. The proofs we construct have objective validity, but it does make mathematics temporally indexed in a way that feels strange. Despite these challenges, intuitionism is a serious position, and it offers a third way between Platonism and formalism. It says mathematics is neither discovered nor is it a meaningless game. It's constructed, created by minds, but not arbitrarily. The constructions must satisfy constraints. They must be rigorous, justified, provable. Mathematics is a human activity, thoroughly mental, but that doesn't make it any less real or meaningful. As you're drifting tonight, think about this. When you imagine a triangle, you're not seeing an abstract form. You're creating an image in your mind. That mental image is fleeting, imperfect, unique to you. But the process of imagining, the way you construct the idea of a triangle that's shared across humans. We all can imagine triangles, reason about them, prove things about them. For the intuitionist, mathematics lives in this shared space of constructive mental activity. It's subjective in origin, but objective in its results. Invented by minds, but not arbitrary. Human, but also universally accessible to any thinking being. It's a beautiful idea, even if it comes with costs. And as we continue exploring, we'll see that the landscape of possible views is even richer than these three major positions suggest. The middle ground, structuralism and other views. By now, you might be feeling pulled in multiple directions. Platonism has its appeal, the idea that mathematical truths are eternal, discovered, independent. Formalism offers a no-nonsense alternative. Math as a game of symbols, invented and purely formal. Intuitionism tries to ground mathematics in human mental activity while maintaining some objectivity. But these aren't the only options. There's a rich landscape of intermediate positions, attempts to capture the best aspects of multiple views while avoiding their pitfalls. One of the most influential contemporary positions is called structuralism. The structuralist says, we've been asking the wrong question. We've been asking whether mathematical objects like numbers exist. But what matters isn't individual objects. What matters is structure, patterns, relationships. Think about the natural numbers. 1, 2, 3, 4, and so on. What is the number 3? The structuralist says there's no answer to that question in isolation. 3 isn't a thing unto itself. It's a position in a structure, the natural number structure. It's the thing that comes after 2 and before 4 that can be expressed as 1 plus 1 plus 1, that has certain relationships to other numbers in the structure. To understand this, imagine the natural numbers as a ladder. What matters isn't what the rungs are made of, wood or metal or abstract forms. What matters is the ladder's structure, how the rungs relate to each other. Each rung is connected to the one above and below. There's a bottom rung, the number 1 or 0, depending on your convention. You can climb up indefinitely. The structure is what's important, not the rungs themselves. This has a surprising consequence. Any system that has the same structure as the natural numbers is, mathematically speaking, just as good as the natural numbers themselves. If you represented numbers with patterns of strokes, with Roman numerals, with positions of an abacus, with states of a computer, as long as the structure is preserved, you're still dealing with the natural numbers. The numbers aren't specific objects. They're roles in a pattern. Structuralism comes in different flavors. Some structuralists, called anti-REM structuralists, believe that structures themselves exist abstractly, independently of any systems that exemplify them. The natural number structure exists whether or not there are any concrete instances of it. This is close to Platonism, except what exists isn't individual mathematical objects, but whole structures. Other structuralists, called in restructuralists, believe structures exist only insofar as they're instantiated in concrete systems. The natural number structure exists because there are systems that exemplify it. Physical systems like arrangements of pebbles, or states of neurons, or configurations of computer memory. No instantiations, no structure. Still others, post-REM or nominalist structuralists, try to avoid committing to the existence of structures at all. They say mathematical statements are really claims about patterns that could be exemplified, not about entities that do exist. What's appealing about structuralism? It explains a lot. It explains why different number systems, base 10, base 60, Roman numerals, can all represent the same mathematics, because they're all exemplifying the same structures. It explains why mathematical truths are necessary, not contingent. The structure of the natural numbers determines that 3 plus 4 equals 7. It's not that there's an abstract object 3 with an abstract object 4 combining to make an abstract object 7. It's that the structure dictates this relationship. Structuralism also makes sense of mathematical practice. Mathematicians often say they're studying structures, not objects. A group theorist doesn't care about specific groups as individual entities. She cares about group structure, about the patterns and properties that all groups share. An analyst doesn't care whether the real numbers are constructed from Dedekind cuts or Cauchy sequences or something else. She cares about the structure of the real numbers, the fact that they form a complete ordered field. But structuralism has its critics. One problem is sometimes called the identity problem. If mathematical objects are just positions in structures, and if there are multiple structures that a given object could belong to, how do we pin down identity? Is the number 3 in the natural numbers the same as the number 3 in the integers? They play the same role in their respective structures, but are they the same object? The structuralist has to either say yes, in which case, how do we understand one object being in multiple structures, or say no, in which case we've multiplied entities beyond what seems necessary. There's also a concern that structuralism just pushes the metaphysical question back a level. Okay, so mathematical statements are about structures, not objects. But do structures exist? If yes, we're back to Platonism, just one level higher. If no, then what are mathematical statements about? Beyond structuralism, there are other intermediate positions worth mentioning. Aristotelian realism holds that mathematical objects exist, but not in an abstract realm. Instead, they exist as properties of physical things. The number 3 exists as the property shared by all collections of 3 things. Circularity exists as the property shared by all circular objects. This avoids the epistemological problem of Platonism. We can know about mathematical properties because we perceive physical objects that have these properties, but it raises questions about infinite mathematics. Can there really be a physical property corresponding to the number 10 to the 100, a googol, when there might not be that many physical objects in the universe? Another view is called fictionalism. The fictionalist says mathematical statements are literally false because they purport to refer to objects that don't exist. Just like Sherlock Holmes lives on Baker Street is technically false because Holmes doesn't exist. But mathematical statements are useful fictions, tools for organizing our thinking and doing science, even though they're not literally true. Some fictionalists go further and argue that even though mathematical statements are false if taken literally, they're true within the fiction of mathematics, just like Holmes lives on Baker Street is true within the fiction of Conan Doyle's stories. Yet another view is the embodied mind approach, popular among cognitive scientists. This view holds that mathematical concepts are grounded in our physical experience and the structure of our brains. We have a natural number sense, an intuitive ability to distinguish small quantities because our brains evolved to process quantity information. More complex mathematics builds on this foundation through metaphorical extension and abstraction. So mathematics is neither platonically discovered nor arbitrarily invented. It emerges from the structure of human cognition interacting with the physical world. This view explains some things nicely. It explains why basic arithmetic is intuitive and why all cultures develop some form of number system. It explains why certain mathematical concepts, like straight lines or symmetry, are easier to grasp than others. They're grounded in perceptual experience. But it also raises questions. If mathematics is based on human cognition, does that mean another species with different cognitive architecture would develop different mathematics? And if so, is there still an objective mathematical truth, or is mathematics relative to cognitive systems? Each of these views, structuralism, Aristotelian realism, fictionalism, the embodied mind approach, is trying to navigate between the extremes of Platonism and outright invention. They're trying to honor the feeling that mathematics is objective and necessary while avoiding metaphysical commitments to abstract objects existing in some strange realm beyond space and time. They're trying to account for the fact that mathematics is a human activity, developed by humans, expressed in human notation, and yet it seems to describe truths that transcend any individual human or culture. The landscape is rich. There's no consensus. Different mathematicians and philosophers find different positions more or less plausible, depending on what they value. Do you care most about explaining the phenomenology of mathematical discovery? Then maybe Platonism. Do you want metaphysical parsimony, avoiding unnecessary entities? Then maybe nominalism or fictionalism. Do you want to ground mathematics in something concrete? Then maybe Aristotelian realism or the embodied mind approach. Do you think structure is what really matters? Then structuralism. As you're sinking deeper into rest, consider this. Maybe the reason there's no consensus is that the question itself is based on a false dichotomy. Maybe mathematics is both discovered and invented. Maybe different aspects of mathematics fall on different sides of this divide. Maybe the whole framework of asking, does math exist, is too simplistic, and reality is more subtle than our categories allow. We'll return to this idea. But first, there are a couple of specific cases worth examining in detail. Two examples from the history of mathematics that illuminate the discovery versus invention debate in particularly interesting ways. The first is zero. The second is imaginary numbers. Let's explore them. The Zero Revolution, a case study in invention. Zero. It seems so simple, so obvious. The number that represents nothing, the starting point on the number line, a placeholder in our positional notation system. We use it constantly, hardly thinking about it. But zero is actually one of the strangest and most profound inventions in the history of mathematics. And its history sheds light on our central question: is mathematics discovered or invented? The thing is, many ancient civilizations didn't have zero. They managed quite well without it. The Egyptians, with their sophisticated understanding of geometry and their ability to build pyramids, had no zero. The Romans, who engineered aqueducts and roads spanning an empire, used Roman numerals, which had no zero. The ancient Greeks, who gave us Euclidean geometry and made enormous mathematical advances, had no zero in their number system. These civilizations could count, they could calculate, they could do multiplication and division, though it was cumbersome. But they didn't have a symbol for nothing. They didn't think of nothing as a number. And when you think about it, that's understandable. Numbers are for counting things. If you have no things, what's there to count? Why would you need a number for that? But the lack of zero created problems, especially in positional notation. In a positional system, like our modern decimal system, the position of a digit affects its value. The 2 in 20 means 2 tens. The 2 in 200 means 2 hundreds. But how do you write 20 or 200 if you don't have a symbol for the empty positions? The Babylonians faced this issue. They used spaces, leaving gaps in their cuneiform to show where a position was empty. But spaces are ambiguous. Is this number 3 or 30 or 300? You have to infer from context. Eventually, by around the 3rd century BCE, the Babylonians started using a special symbol to mark empty positions. This was a step towards zero, but it wasn't quite zero as a number. It was a placeholder, a way of saying nothing here, not a quantity in its own right. The Mayans independently developed something similar, a shell-shaped symbol in their base 20 system to mark empty positions. But the full conceptual breakthrough came in India, probably around the 5th to 7th century CE. Indian mathematicians like Brahmagupta didn't just use zero as a placeholder. They treated it as a number, a quantity that could be manipulated like any other. You could add zero to a number and get the same number back. You could subtract a number from itself and get zero. You could even, and this was radical, perform operations with zero itself. Brahmagupta wrote down rules. 0 plus 0 is 0. 0 times any number is 0, and so on. There were complications. What is 0 divided by 0? Or any number divided by 0? These questions led to deep investigations, ultimately resulting in the understanding that division by 0 is undefined or infinite, depending on the context. But the crucial point is that 0 became a number, a full-fledged member of the mathematical family. This changed everything. With 0, positional notation became unambiguous. You could write 20 as 20, clearly distinguishing it from 2 or 200. Arithmetic became simpler, more streamlined, and conceptually, a door opened. If nothing could be a number, then mathematics wasn't just about counting physical objects. It was about abstract relationships, patterns, operations. Mathematics became more about process and structure, less about things. The concept of zero spread from India to the Islamic world, where mathematicians eagerly adopted it. Al-Khwarizmi, whose name gave us the word algorithm, used zero in his arithmetic and algebraic works. From the Islamic world, zero came to Europe, gradually replacing Roman numerals for calculation, though that process took centuries. Merchants and scholars who learned the new number system found it vastly superior. By the Renaissance, the Hindu-Arabic numerals, including zero, had triumphed. So here's the question. Was zero discovered or invented? On one hand, zero seems like an invention. No ancient civilization had it until Indian mathematicians created it. It was a deliberate conceptual innovation, a decision to treat nothing as something, to give absence a symbol and make it manipulable. Different cultures could have continued without it, indeed, did continue for centuries. There's nothing in nature that forces you to have zero. You don't find 0 sheep or 0 apples in the world. Zero is an abstraction, a human creation. On the other hand, once zero was invented, mathematicians discovered things about it. They found that zero has properties, necessary properties that follow from its definition. Zero plus anything is that thing. Zero times anything is zero. These aren't arbitrary choices. They're logical consequences of what zero means. If you change these rules, you break the coherence of arithmetic. So in some sense, even though zero was invented, its properties were discovered. Moreover, zero turned out to be indispensable. It's not just a convenient notational trick. It's fundamental to mathematics. You can't do algebra properly without zero. You can't develop calculus without zero. The concept of a limit approaching zero is central to analysis. Negative numbers don't make full sense without zero as a dividing point between positive and negative. Zero is woven into the fabric of mathematics so deeply that it's hard to imagine mathematics without it. And zero's usefulness in science is profound. Temperature scales have 0 points, absolute zero in physics, the point where thermal energy is minimized. Coordinates in geometry often use zero as an origin. Null results in experiments finding nothing are meaningful scientific findings. The concept of zero, once it existed, turned out to apply everywhere. So maybe zero was invented as a notation, but discovered as a concept. Indian mathematicians invented the symbol, the decision to treat nothing as a number. But in doing so, they uncovered a pre-existing mathematical structure, a place in the number system that had always been there, waiting to be recognized. Or maybe not. Maybe zero really is a human creation, and its properties, while logically constrained, are still features of a system we built. The Platonist will see zero as revealing an eternal truth. The anti-Platonist will see it as a brilliant human innovation that turned out to be useful. Both can agree on the history and the mathematics while disagreeing on the metaphysics. This is the puzzle in microcosm. Zero, such a simple thing, encapsulates the entire debate. It feels both invented and discovered. Its history is clearly human, contingent, cultural, but its role in mathematics feels necessary, inevitable, true. Maybe the answer is that asking, is zero discovered or invented, is the wrong question. Maybe it's both. Maybe the dichotomy breaks down when you look closely. Let's turn now to another case, one that's even stranger. A number that mathematicians literally called impossible, that seemed to make no sense, that was invented out of pure desperation and convenience, and yet turned out to be indispensable to mathematics and science. Let's talk about imaginary numbers and human creativity. If zero seems like a strange number, what do you make of the square root of -1? This number, if you can even call it a number, doesn't exist on the number line. It can't be positive, because a positive number squared gives a positive result. It can't be negative, because a negative number squared also gives a positive result. -1 times. -1 is +1. So what could the square root of -1 be? For centuries, mathematicians said it's nothing. It's meaningless, impossible, absurd. The square root of -1 does not exist. And yet, by the 16th century, Italian mathematicians were finding that if they allowed themselves to work with this impossible quantity, even just temporarily in the middle of a calculation, they could solve equations they otherwise couldn't solve. Girolamo Cardano, in his 1545 work Ars Magna, encountered square roots of negative numbers while solving cubic equations. He found them disturbing, called them sophistic. but noted that manipulating them according to certain rules could lead to correct answers. He was doing something that seemed nonsensical, working with quantities that couldn't exist, but the results were valid. How Raphael Bombelli, a bit later, worked out more systematic rules for these impossible numbers. If you define I, the imaginary unit, as the square root of -1, then you can perform arithmetic with it. I times I is -1. I times a regular number, call it a real number, gives you an imaginary number. You can add real numbers and imaginary numbers to get complex numbers. Numbers, the real part, and an imaginary part, like 3 plus 2, I. This all seems like pure invention. There's no natural phenomenon that obviously corresponds to imaginary numbers. You can't have I apples. Imaginary numbers were created to fill a gap, to make certain equations solvable, to give solutions where none existed before. And for a long time, mathematicians were uncomfortable with them. They called them imaginary, not as a neutral term, but as a dismissive one. These aren't real numbers. They're fictitious, creatures of algebraic manipulation. And yet, imaginary numbers refused to go away. Every time mathematicians tried to avoid them, they snuck back in. Solving cubic equations required passing through imaginary numbers, even if the final answer was real. The fundamental theorem of algebra, which states that every polynomial equation has solutions, only works if you allow complex numbers. Otherwise, simple equations like x squared plus 1 equals 0 have no solutions. So mathematicians grudgingly accepted them. But they still felt invented, artificial, merely useful fictions. Then something remarkable happened. Imaginary numbers turned out to have geometric meaning. On a number line, you can represent real numbers as points, positive numbers to the right, negative to the left. But where do imaginary numbers go? They don't fit on the line, but they do fit in a plane. If you make a two-dimensional coordinate system with the real numbers on the horizontal axis and imaginary numbers on the vertical axis, complex numbers become points in this plane. The number 3 plus 2 I is the point 3 units to the right and 2 units up. This is called the complex plane, or the Argand diagram, after Jean-Robert Argand, who popularized it in the early 19th century. In this representation, complex numbers aren't so strange anymore. They're just two-dimensional numbers, ordered pairs, and operations on complex numbers have geometric interpretations. Multiplying by I rotates a point 90 degrees counterclockwise. Complex numbers encode rotations and scalings in the plane. They're a natural way to do two-dimensional geometry and trigonometry. And then the applications exploded. Complex numbers are essential in electrical engineering for analyzing alternating current circuits. Waves, oscillations, anything periodic are best described using complex exponentials. Quantum mechanics, the most fundamental theory of matter we have, is formulated in terms of complex numbers. The wave function, the core object in quantum theory, is complex valued. You can't do quantum mechanics without imaginary numbers. Signal processing uses complex numbers. Control theory uses complex numbers. Fluid dynamics uses complex numbers. Complex analysis, the study of functions of complex variables, is one of the most beautiful and powerful branches of mathematics, with applications throughout physics and engineering. So here's this thing that was invented, named imaginary, to emphasize its fictitiousness. treated as a mere algebraic trick for centuries. And it turns out to be indispensable. It describes reality. It predicts experimental results. It's woven into the fundamental structure of the universe. If quantum mechanics is to be believed, was the square root of -1 invented or discovered? It's hard to say it was discovered in the traditional sense. There's no obvious natural phenomenon that is imaginary. And for centuries, mathematicians had to convince themselves it was okay to use imaginary numbers. It feels invented. But once allowed into mathematics, imaginary numbers revealed structures and connections no one anticipated. They weren't arbitrary. They had properties, they fit into a coherent framework, they solved problems, they unified disparate areas of mathematics. It's as if imaginary numbers were always there, latent in the structure of mathematics, waiting for someone to be bold or desperate enough to take them seriously. The Platonist might say that complex numbers exist in the realm of mathematical forms, and Cardano and others discovered them, even though they initially misunderstood their nature. The anti-Platonist might say that complex numbers are a human creation, extended from real numbers by a clever definition, and their usefulness is a matter of historical contingency and the particular structure of our physical theories. But both sides have to account for the strangeness of the story. Imaginary numbers were invented reluctantly, almost against mathematicians' better judgment, as a stopgap, a formal trick. And they turned out to be essential, not just useful, but seemingly required by nature. If mathematics is entirely invented, how do we explain this? If mathematics is entirely discovered, how do we explain the centuries of skepticism and the sense that imaginary numbers were being stipulated into existence? Maybe the answer is that mathematical invention and discovery are not opposites, but two stages of the same process. We invent notations, definitions, systems. We extend our mathematical language to handle new situations. But in doing so, we discover consequences, structures, connections that we didn't anticipate and couldn't have dictated. We invent the axioms of group theory, but we discover that groups have subgroups, normal subgroups, homomorphisms, all with specific properties. We invent complex numbers, but we discover the Cauchy integral theorem, the residue theorem, entire functions, the richness of complex analysis. So perhaps asking, did we invent it or discover it, is too binary. Perhaps every significant mathematical development involves both invention and discovery, intertwined so closely that separating them is artificial. As you let these thoughts wash over you, sinking into sleep, consider this. The history of zero and imaginary numbers shows us that mathematics is not a fixed, eternal structure. We're simply uncovering piece by piece. It's dynamic, evolving, responsive to human creativity and need. But it's also not arbitrary. Not anything goes. The structures we build have to cohere. They have to work. They have to satisfy constraints that we don't control. We participate in mathematics. We shape it and are shaped by it, but we don't determine it unilaterally. This is the paradox at the heart of mathematics, and it's why the question, does math exist or did we invent it, doesn't have a simple answer. The answer might be yes to both, or neither, or something else entirely. Let's keep exploring. The neuroscience angle. Math in the brain. Let's step back from abstract philosophy for a moment and look at something more concrete. How does the human brain actually process mathematical concepts? What happens in your neurons when you think about numbers? And what does this tell us about whether mathematics is discovered or invented? Over the past few decades, neuroscientists and cognitive psychologists have learned a lot about mathematical cognition, and some of their findings are surprising. It turns out that humans, and even some animals, have an innate, built-in sense of number. Not the ability to count in the formal sense, but an intuitive capacity to distinguish between different quantities. This is called the approximate number system, or number sense. Infants as young as 6 months can tell the difference between 8 dots and 16 dots. They can't count, they don't have language, they certainly don't have formal mathematical training, but they can distinguish larger from smaller quantities. This ability persists into adulthood. If you flash arrays of dots on a screen too quickly for someone to count, they can still estimate which array had more dots, especially when the difference is large. This number sense isn't perfect. It's approximate, getting worse as the numbers get larger or closer together. But it's universal across cultures and present from birth. This suggests that basic numerical intuition is hardwired into the human brain, the result of evolutionary pressures. Our ancestors who could quickly estimate which tree had more fruit or which group of predators was larger would have had a survival advantage. Interestingly, other animals have this too. Experiments show that monkeys, rats, even fish and birds can distinguish quantities. A lioness can assess whether her pride is outnumbered by rival lions. Crows can remember how many pieces of food are hidden in different locations. This suggests that the number sense is evolutionarily ancient, not unique to humans, arising because accurately perceiving quantity is useful. Neuroimaging studies show that specific brain regions are involved in numerical processing. The intraparietal sulcus, a region in the parietal lobe, consistently lights up when people do numerical tasks, whether estimating quantities, comparing numbers, or even just seeing numerals. This region seems to be the seat of our basic number sense. But here's where things get interesting for our philosophical question. If basic numerical cognition is innate and biological, does that support the view that mathematics is discovered? The Platonist might argue that yes, it does. Our brains are structured to perceive quantity because quantity is a real feature of the world. Just as our eyes evolved to perceive light because light exists, our number sense evolved to perceive numerical relationships because those relationships are objectively real. We discover mathematics because our brains are attuned to mathematical structure in the world. Or does innate numerical cognition support the view that mathematics is invented? The anti-Platonist might argue that yes, it does. Mathematics isn't about an abstract realm. It's about how our brains structure and process information. We have a number sense because our ancestors needed to navigate a complex environment, and categorizing things into discrete quantities was useful. Mathematics is an extension and formalization of these cognitive capacities. We invent mathematical systems that align with how our brains naturally work. Cognitive scientists like George Lakoff and Rafael Nunez have argued for this latter view in their book, Where Mathematics Comes From. They propose that all mathematical concepts, even abstract ones, are grounded in bodily experience and cognitive metaphors. We understand numbers via experiences like putting objects in piles. We understand infinity via experiences of motion and extent. Even pure abstractions like sets or functions are ultimately based on metaphorical extensions from concrete experiences. In this view, mathematics is a human creation through and through, but not an arbitrary one. It's constrained by the structure of human cognition, by how our brains work. Different species with radically different cognitive architectures might develop different mathematics. But within the human lineage, mathematical concepts have a universality because we all share the same basic cognitive toolkit. This embodied mind approach has some appeal. It explains why certain mathematical ideas are easier to grasp than others. They're closer to our bodily experience. It explains why different cultures all developed arithmetic, because the cognitive capacities underlying arithmetic are universal. It explains cross-cultural similarities in mathematical reasoning without needing to posit an abstract realm of mathematical objects. But there are challenges. For one thing, it's not clear that all of mathematics can be grounded in bodily metaphors. Is the concept of a Hilbert space or a Lie algebra really based on metaphorical extension from physical experience? Maybe, but the chain of metaphorical reasoning gets very long and tenuous. At some point, it seems like we're doing genuine abstraction, moving beyond anything in our bodily experience. Moreover, even if mathematical concepts are grounded in cognitive structures, that doesn't mean mathematical truths are subjective or culture relative. The cognitive structure might be universal, leading all thinking beings, or at least all beings with similar cognition, to the same mathematics. And the fact that mathematics so effectively describes the physical world suggests that our cognitive structures are aligned with the structure of reality, which brings us back toward something like Platonism, just one level removed. There's also cross-cultural variation that's interesting. While basic numerical cognition is universal, how cultures conceptualize and use numbers varies. Some languages, like Piraha, have only approximate number words, no precise counting beyond 1, 2, and many. Speakers of these languages have normal number sense, but don't develop formal arithmetic. Does this show that arithmetic is a cultural invention, not a universal discovery? Or does it just show that formal systems require cultural transmission even if the underlying concepts are universal? Studies also show that expertise in mathematics changes the brain. Mathematicians' brains respond differently to mathematical statements than non-mathematicians' brains. With practice, mathematical reasoning becomes more efficient, engaging different neural pathways. This is true of any skill. Musicians' brains are different from non-musicians' brains, but it shows that doing mathematics is a learned activity, not purely innate. All of this neuroscience and cognitive science paints a complex picture. Yes, we have innate numerical capacities, but those capacities are just the starting point. Formal mathematics requires learning, cultural transmission, notation systems, abstract thinking. The biology provides a foundation, but the edifice of mathematics is built by human effort. Does this settle the question of whether mathematics is discovered or invented? Not really. It tells us that human cognition plays a role, which was obvious but now confirmed in detail. But it doesn't tell us whether the truths mathematics describes exist independently. Our brains might be tuned to perceive mathematical structure, because that structure is real. Or we might impose mathematical structure on our experience because of how our brains work. The neuroscience alone can't distinguish these interpretations. What it does do is remind us that mathematics is done by embodied biological creatures with particular evolutionary histories and cognitive architectures. We're not disembodied minds accessing a Platonic realm. We're animals with brains, and our mathematics is shaped by that. But whether the mathematics we create or discover transcends our particular biology, that question remains open. As you drift further towards sleep, think about your own mathematical experiences. When you add 2 and 2, when you visualize a shape, when you follow a logical argument, something is happening in your brain. Neurons are firing, patterns are forming. This is the substrate of mathematical thought. But does that mean mathematics is nothing more than neural activity? Or does your brain provide access to truths that exist beyond it? The neuroscience can't tell you. You'll have to decide for yourself, if you decide at all. Maybe the question can rest unanswered, a gentle puzzle to ponder on the edge of sleep. The multiverse of mathematics. Here's a thought to drift off on. Could mathematics be different? Not just the notation or the cultural practices around mathematics, but the actual mathematical truths. Could 2 plus 2 equal something other than 4? Could the Pythagorean theorem be false? Could there be geometries that don't even have triangles? At first, this sounds absurd. Mathematical truths seem necessary. 2 plus 2 equals 4 in all possible worlds. It's not a contingent fact like water is H2O or the speed of light is approximately 300,000 kilometers per second, which could have been different if the universe had different laws. Mathematical truths are necessary truths. They couldn't be otherwise. But wait, look at geometry. For over 2,000 years, Euclidean geometry was the geometry. Euclid's Elements laid out 5 postulates, basic assumptions, from which all of plane geometry could be derived. Parallel lines never meet. The angles in a triangle sum to 180 degrees. These seemed like obvious, necessary truths about space. But then, in the 19th century, mathematicians started exploring what would happen if you changed one of Euclid's postulates, specifically the 5th postulate, the parallel postulate, which states that through a point not on a given line, there is exactly one line parallel to the given line. What if that weren't true? What if there were no parallel lines, or infinitely many? Mathematicians like Gauss, Bolyai, and Lobachevsky developed geometries where the parallel postulate is false. In hyperbolic geometry, through a point not on a line, there are infinitely many lines that never intersect the given line. In elliptic geometry, there are no parallel lines at all. All lines eventually intersect. And remarkably, these geometries are consistent. They don't lead to contradictions. They're just different. And even more remarkably, these non-Euclidean geometries turned out to describe physical reality. General relativity says that space-time is curved, and the geometry of curved space-time is non-Euclidean. So which geometry is true? It depends on what you're describing. On a flat surface, Euclidean. On the surface of a sphere, elliptic. In hyperbolic space or near massive objects, hyperbolic or more complex geometries. This shows that mathematical truths can depend on your axioms, your starting assumptions. Change the axioms, get different theorems. So, is mathematics relative to axiom systems? Does mathematics not have universal truths, but only truths relative to frameworks? The formalist would say yes. Mathematics is about deriving consequences from axioms. Different axiom systems give different mathematics. There's no absolute sense in which Euclidean geometry is true and hyperbolic geometry is false. Both are consistent, both are valid mathematics. They're just different games, played by different rules. The Platonist has to work harder here. One response is to say that all possible consistent mathematical systems exist in the Platonic realm. Euclidean geometry exists. Hyperbolic geometry exists. Every consistent set of axioms defines a mathematical structure that exists. So there isn't one geometry. There's a whole landscape of geometries. We discover which one applies to our physical universe through observation, but they all exist mathematically. This is actually a version of Platonism called full-blooded Platonism. It says that every coherent mathematical structure exists. If you can write down consistent axioms, the structure they describe is real. This view has the advantage of explaining why so much abstract mathematics turns out to be useful. Everything exists, so whatever the universe needs, there's mathematics for it. But it also seems extravagant. It multiplies entities to an absurd degree. Not only do all the natural numbers exist, and all the real numbers, and all the sets, but also every possible mathematical structure that could be consistently defined. That's a lot of existence. Still, this view addresses the question of whether mathematics could be different. Yes, it could be different in the sense that there are alternative mathematical systems. But no, it couldn't be different in the sense that the structures themselves, once defined, have necessary properties. Euclidean geometry is what it is, necessarily. Hyperbolic geometry is what it is, necessarily. You can choose which system to work in, but you can't change the internal truths of that system. There's another sense in which mathematics might be different. Could there be mathematical truths that are true but unprovable? Could there be questions that have answers, but we'll never know them? Enter Kurt Gödel again. We mentioned him earlier when discussing formalism. Gödel's incompleteness theorems, proved in 1931, show that in any consistent formal system capable of expressing arithmetic, there are true statements that can't be proved within the system. This is startling. There are mathematical truths that are beyond proof. Now, true here, it's a bit tricky. What does it mean to say a statement is true if it's not provable? In one interpretation, we can define a standard model of arithmetic, the natural numbers as we normally understand them, and a statement is true if it holds in this model. Even if we can't prove it from the axioms, it's still true in the intended interpretation. But this raises a problem. If truth outstrips proof, then there are mathematical facts we can never know for certain. We might have intuitions or beliefs, but we can't have proofs. Does this mean mathematics is incomplete? That there are truths forever beyond our grasp? Some mathematicians and philosophers find this unsettling. The Platonist might be comfortable with it. Sure, there are mathematical truths we can't prove. Mathematical reality is vaster than our formal systems. We'll discover what we can, but the realm of mathematical truth is inexhaustible. The formalist, on the other hand, has a harder time. If truth is supposed to be provability within a system, then unprovable statements aren't true. They're undecided. But Gödel's theorem suggests they are true in the model, even if undecided in the formal system. This all leads to a vertiginous thought. Maybe there's a vast landscape of possible mathematics. Different axiom systems, different logics, different structures. In one corner, Euclidean geometry. In another, hyperbolic. In yet another, systems of arithmetic where Gödel's undecidable statements are taken as axioms and new theorems are derived. The landscape is infinite, branching endlessly, and maybe our mathematics, the mathematics we've developed, is just one path through this landscape. Other paths are possible. Other civilizations on other planets with different needs and different cognitive structures might explore different parts of the landscape. Their mathematics would be consistent, rigorous, useful for them, but different from ours. Or maybe not. Maybe the landscape, though vast, has a certain structure to it. Maybe any sufficiently advanced mathematics would discover the natural numbers, the real numbers, basic geometry, basic algebra. Maybe these are universal waypoints, and all intelligent beings converge on them. Maybe the landscape has a canonical core, and the differences are just peripheral elaborations. We don't know. We can't know without encountering other mathematical civilizations and comparing notes. But the possibility that mathematics could be different, that there are alternative mathematics, raises the stakes of our original question. If mathematics is discovered, then presumably there's one true mathematics, the structure of the Platonic realm. But if mathematics is invented, then multiple mathematics are possible, each valid in its own right. Yet even the existence of alternative mathematics doesn't settle the question, because each alternative, once defined, has its own internal necessary truths. You might choose different axioms, but you can't choose the theorems. They follow necessarily. So invention and discovery are still intertwined. As you sink into dreams, imagine this infinite landscape of mathematics. Peaks and valleys of different structures, pathways through forests of theorems, rivers of proof flowing from axiom springs to theorem seas. Humans have explored only a small portion. Most of it remains unknown, perhaps unknowable. Whether it existed before we arrived or came into being as we explored, that's the mystery. And maybe it's a mystery that can rest unsolved, a question that doesn't need an answer, only appreciation for the strangeness of it all. When math fails, the boundaries. We've been talking about the effectiveness of mathematics, how unreasonably well it describes the physical world. But let's be honest, there are many areas where mathematics doesn't work as well, where the precision and predictive power that physics enjoys are simply not available. Understanding these limits tells us something important about the nature of mathematics and its relationship to the world. Consider biology. Biology uses mathematics, certainly. Population dynamics are described with differential equations. Genetics uses probability and statistics. Molecular structures are analyzed with geometry and topology. But biology doesn't have the kind of fundamental mathematical laws that physics does. There's no biological equivalent of Newton's laws or Maxwell's equations. You can't write down a few equations and derive all of biology from them. Why not? Because biology is messy. It's historical, contingent, full of exceptions. Evolution doesn't optimize in the way physical systems minimize energy. Living systems are incredibly complex, with countless interacting components at multiple scales. And crucially, Living things are shaped by their history, by evolutionary accidents and environmental changes that could have gone differently. Biology is path-dependent in a way that physics isn't. This doesn't mean biology is less scientific or less rigorous. It means it's a different kind of science, one where mathematical description is more approximate, more statistical, less deterministic. And this raises a question. If mathematics is the language of nature, the structure of reality, why does it work so well for physics and less well for biology? Is biology somehow less fundamental, less real? That seems wrong. Or consider economics. Economics is heavily mathematical. Economists build models, derive equilibria, prove theorems. But economic models routinely fail to predict real-world behavior. The 2008 financial crisis was not predicted by the mathematical models economists relied on. In fact, those models may have contributed to the crisis by giving a false sense of security. Why do economic models fail when physical models succeed? One answer is that economic systems involve human behavior, which is complex, adaptive, and influenced by expectations. When people expect a recession, they change their behavior, which affects whether a recession occurs. This is called reflexivity, and it means economic systems are not like physical systems. A planet doesn't change its orbit because you predicted its orbit, but an economy can change because you predicted economic outcomes. Moreover, humans are strategic. We try to anticipate what others will do and adjust accordingly. This leads to game-theoretic complications that don't arise in physics. There's no analog of a strategic electron that tries to outwit the experimenter. So economics is fundamentally harder to mathematize than physics, not because economists are worse at math, but because the subject matter resists it. Sociology, psychology, political science all face similar challenges. These fields use mathematics, but not with the precision and predictive success of physics. They're studying systems that are complex, adaptive, historical, reflexive. Mathematical models in these fields are valuable for clarifying assumptions, deriving logical consequences, and providing rough predictions. But they don't achieve the exquisite accuracy of physics. What does this tell us about mathematics? One possibility is that mathematics describes only certain kinds of systems, simple systems or systems that can be approximated as simple, isolated systems that can be studied without too much interference from their environment, non-adaptive systems that don't change their behavior in response to being studied. Physics focuses on these kinds of systems, and that's why mathematics works so well. Other fields study different kinds of systems, and for these, mathematics is less effective, not useless, but limited. This would suggest that mathematics isn't the universal language of nature. It's the language of a certain kind of nature, the relatively simple, non-adaptive, non-historical kind. Another possibility is that all systems, in principle, can be described mathematically, but the mathematics required for complex systems is beyond our current capacities. Maybe there's a mathematical theory of biology that's as precise as quantum mechanics. We just haven't discovered it yet. Maybe economics could be fully mathematized if we had the right framework. This view maintains the universality of mathematics, but admits that we've only scratched the surface. Or maybe the lesson is humility. Mathematics is a human tool, powerful but not omnipotent. It works brilliantly in some domains and less well in others. And that's okay. We shouldn't expect one method, one language, to capture everything. Different domains require different approaches. Physics, mathematics, biology, a mix of mathematics, narrative, and historical explanation. The human sciences, a mix of statistics, qualitative understanding, and interpretation. From a philosophical standpoint, the limited effectiveness of mathematics in some domains complicates the Platonist view. If mathematics describes an independent reality, and that reality is the structure of the universe, why doesn't it describe all aspects of the universe equally well? Why is it so effective for fundamental physics and less so for complex systems? The Platonist might respond that physics studies the fundamental mathematical structure, the deepest level of reality. Complex systems like economies or ecosystems are emergent, built on top of this fundamental structure, but with additional contingent details that aren't purely mathematical. So mathematics describes the base layer perfectly, but higher level phenomena have other aspects. The anti-Platonist might see the limited effectiveness differently. Mathematics is a tool we invented for certain purposes, describing physical systems being one. It works well where it works, because we designed it to. Where it doesn't work as well, we either haven't designed the right mathematics yet, or the domain doesn't fit the tool. That's not a failure of the tool. It's a recognition that different problems require different tools. There's also something called the streetlight effect. A drunk man searches for his lost keys under a streetlight, not because he lost them there, but because that's where the light is. Maybe we find mathematics effective in physics, not because physics is uniquely mathematical, but because we study physics in ways that foreground the mathematical aspects. We focus on systems that are amenable to mathematical description and ignore or downplay aspects that aren't. So the effectiveness is partly an artifact of how we choose to do science. This is not to say the effectiveness of mathematics in physics is illusory. It's real and impressive, but it might not be as mysterious as it seems. We selected physics as the domain where mathematical description is most feasible, and then we're surprised that mathematics works well there. Of course it does. That's why we call it physics. As you rest, consider this. The universe is vast, rich, multifaceted. Mathematics captures some aspects beautifully, precisely, powerfully. But there are other aspects, the living, the adaptive, the conscious, the historical, that resist full mathematical description. Maybe these aspects are just as real, just as fundamental as the mathematical ones. Maybe reality is bigger than mathematics. And maybe that's not a problem, but a feature, a reminder that the world is stranger and more wonderful than any single language can capture.